The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome all to today's session on the new climate change initiative, a resolution uncover map from the European Space Agency. My name is Andrea Manara from the ITU, the International Telecommunication Union. And it is an honor for me to introduce a new episode in the GeoAI History series. We launched this series at the beginning of 2022, and we discussed GeoAI applications and policies, ethics, the future of GI for good. Thematic sessions included climate actions, spatial digital twins, energy, ecology, agriculture, water and food system, health. And more recently, we are focusing on geospatial large language model and GeoAI and education under the leadership of the curator of this series, Maria Brovelli. If you missed some episodes, don't worry, you can watch the recordings of those events on YouTube or in the neural network to which you are connected right now. Without further ado, let me now introduce Maria Brovelli, who will moderate today's event. Maria, ciao.
Ciao,
Maria
Andrea.
is a professor of GIS at the Politecnico di Milano at the Geoinformatics Engineering course of study, and she's a member of the Schools of Doctoral Studies in Data Science and Earth Observation alla Sapienza, Roma alla Sapienza. Amongst her many other activities, Maria is Vice President of the Commission of Geospatial Information of ISPRS, Chair of the UN Global Geospatial Information Management Academic Network, and co-chair of the United Nations Open GIS Initiative. I will now give the floor to Maria. She will introduce the speakers of this session and will moderate the session. Maria, the floor is yours.
Thank you, Andrea, and welcome to everyone. I'm so excited with respect to the webinar today. First of all, because it's really a hot topic. So it's something, this land cover project that will be reused in so many projects related to good, as we think about it. So very important also for many United Nations projects. And then the second point, why it is so relevant, is that machine learning and AI is applied in this project. But I don't want to spend too much time in chatting. Just I want to start introducing the first speaker of today, the first speaker is Clément Aubergel, who is a scientist working at the European Space Agency, Climate and Long-Term Action Division in the UK, and he's focusing more on land surface activities. His division oversees implementing the European Space Agency climate program, the Climate Change Initiative. The climate quality data sets produced by the CCI, this climate change initiative, are a major contribution to the evidence base used to understand the climate change, which drives international action. Before working at the European Space Agency, he held a position in the research department of the European Centre for Medium-Range Weather Forecast, as well as of the French Meteorological Service, working on land surface analysis. His activity at the European Space Agency are mainly shared between the European Space Agency Climate Program and the Program in Support of International Development and the EO Africa and Development Facility, all implemented under the Directorate of Earth Observation Programs. Okay, so Clément, welcome. And I give you the floor for explaining, for giving the overview about this fantastic project.
Molte grazie, Maria. Thank you very much. I will share my screen and hope that you will all see it. Could you please confirm it's fine?
Yes, we do.
Thank you. So, yes, my contribution to this webinar is to present you the context in which this data set on high-resolution land cover has been developed. So I work at EXACT, ESA's home in the UK, that is hosting the Climate and Long-Term Action Divisions. We are ESA's focal point for climate activities, and we represent the agency's interest, working in very close collaboration with the different actors of the international climate landscape to serve science, service, and policy. We lead activities related to climate and long-term cross-disciplinary and strategic Earth observation actions. We are an observer at the IPCC and the UNFCCC, and our main role is to develop and implement ESA's climate program, the Climate Change Initiative. But what is it? Climate change is arguably the greatest environmental challenge facing us in the 21st century. The consequences of a warming climate are far-reaching, and with worsening impacts predicted for the natural environment and society for generations to come, climate change is high on political, strategic, and economic agendas worldwide. Combating climate change requires a global effort. The United Nations Framework Convention on Climate Change, UNFCCC, is leading this international effort to combat climate change and limit global warming to well below 2 degrees Celsius above pre-industrial levels as set out in the Paris Agreement for Climate. But to make decisions on climate change mitigation and climate change adaptation, the UNFCCC requires systematic observations of the climate system. It is only with accurate, high-quality observation at sufficient resolution in both time and space that climate science and climate services will progress. Space-based Earth observation information has the potential to contribute to achieving the Paris Agreement objectives in many ways, including for effective policy making and monitoring policy implementation. And that is precisely why the role of space agencies, of the European Space Agency, is crucial when it comes to climate, when it comes to climate action. The capabilities of Earth observation satellites in support of climate information needs reflect their unique abilities and benefits. Satellite Earth observation have wide area observation. They are global scale, they are non-intrusive, they provide uniformity, rapid measurement, and continuity. They permit to scan, to take the pulse of our planet, and are very complementary to other types of observations, such as from in situ aircraft, buoys, drones, to build a much needed global integrated observing system. and developing world-class Earth observation systems with European and global partners to address scientific and societal challenges is at the core of our activity. That's what we do. ESA has been dedicated to observing Earth from space ever since the launch of its first weather satellite back in 1977. And here on this slide, you have a snapshot of all missions developed and under development in our three main lines of activities: science with the Earth Explorer, meteorology, and Copernicus with its dedicated family of satellites, the Sentinels. Back to ESA's climate program. To better understand the climate system and its variability, the UNFCCC, as I said, needs observations. They have delegated to the GCOS, the Global Climate Observing System, a public consultation to define the variables that represent climate at best, that are critical for characterizing the climate system and its changes. And GCOS have defined a list of 55 essential climate variables, ECVs. More than two-thirds can benefit from satellite Earth observation. And it is as a direct response to the UNFCCC needs in observation that ESA has launched its climate program, the Climate Change Initiative, CCI, more than a decade ago. The CCI is a coordinated research and development program amongst ESA member states that main objective is to generate robust, long-term, global, satellite-derived data set for key indicators of climate change, the essential climate variable. And we do that by putting together 40 years of ESA Earth observation archives and combining them with data from both third-party missions. These are missions that are not owned or operated by ESA, and current missions such as the Sentinel. ECVs can be used to guide mitigation and adaptation measures, to assess climate risks, to attribute climatic events to underlying causes, and to support climate services. Climate modelers use ECVs to study drivers, interactions, and feedbacks due to climate change, as well as teleconnection, tipping point, and fluxes of energy, water, and carbon, and to predict future changes. Something else that is quite important to stress out is that all our data sets, and here on this slide, you have the different projects we are developing under the Climate Change Initiative, are free on our open data portal. You have the website here on the bottom right-hand side of the screen, and you can access those data sets. Just for a few examples, this is for the Soil Moisture CCI project that is putting together data from 17 sensors in space to develop an harmonized time series of surface soil moisture spanning from 1979 to 2022, soon 2023. We process large amount of data, and this often requires advanced techniques. And this is an area where machine learning, where AI is helping a lot. We also have a project dedicated on fire. If we focus on fire in the context of the Paris Agreement for Climate, it's because vegetation on land, when disturbed by wildfire, has a potential to release significant greenhouse gas and particulate matter into the atmosphere. It is estimated that about 25 to 35% of greenhouse gas result from biomass burning, and therefore they are considered an important factor in climate change. Our Fire CCI project focuses on the key variable burn area, using a hybrid approach where they combine surface reflectance and thermal anomaly. Fire CCI has different products at global scale, derived from MODIS, Sentinel-3, AVHR, but has also recently focused on high resolution at regional scale, using Sentinel-2 information at 20 meters spatial resolution to develop a small fire database covering sub-Saharan Africa, for now for 2 years, but we are currently working on how to expand this database both in time and space. Just for sake of illustration, here on the top, you have burn area for the same scene, for the same period, as seen by MODIS, about 300 meters spatial resolution, Sentinel-3, and then Sentinel-2. And you can see that high resolution significantly improves total burn area detection. Now, this information is very useful if we want to ingest it in a fire emission system, a fire emission model. We did an experiment for Austral Africa for 1 year where we tried to derive carbon monoxide, a measure of fire emission, using different input for burn area. On this figure here, in black, you have carbon monoxide observations taken by the Tropomi on board Sentinel-4, Sentinel-5P, sorry. And here in green, you have the fire emissions that are computed when we used high-resolution burn area as an entry. And here, different products at coarse resolution, spatial resolution. So you can really see the impact of having high resolution. We also look at land cover and land cover change, coming more deeper in the topic of today's webinar. The role of land for storing carbon and its future potential for offsetting carbon emission is an area of active research. And modeling the interaction between vegetation, climate, and greenhouse gases is supported by datasets such as those from the moderate and high-resolution CCI land cover project to quantify changes consistently across countries. The moderate resolution land cover project has a unique series of annual consistent land cover map at 300 meters spatial resolution between 1992 and 2021, and the most recent years are currently being produced and should be available very soon. The high-resolution land cover is developing static map for 3 areas for now at 10 meters spatial resolution, along with long-term record of regional maps at 30 meters in the sub-region every 5 years, and information about changes every year. I will, however, stop here my presentation and let my colleagues develop further this very topic. Thank you very much. You unmute, Maria.
Oh, thank you, Clement. Very clear presentation of the CCI in general and also of this project related to land cover, which is the topic of today. But now we want to go to the technical details with respect to this product. And therefore, I want to call here my colleague Lorenzo Bruzzone. Thank you, Lorenzo, for being here. I'm so happy to have you here. So before a short introduction, and then I will give you the word. So Lorenzo Bruzzone is a full professor at the University of Trento, and is the founder and director of the Remote Sensing Laboratory in Trento. His research interests are in the area of remote sensing, radar, SAR, and machine learning. He promotes and supervises research on these topics within the framework of many national and international projects, and among the other projects, there is this one. So he is the science lead for the High Resolution Land Cover project in the framework of the Climate Change Initiative of the European Space Agency. Besides that, he's author of more than 380 scientific publications. He referred journals and many others in book chapters and conferences. He got many international and national awards related to his scientific activity. He's a co-founder of the IEEE International Workshop on the analysis of multi-temporal remote sensing images. Multitemp is the founder of IEEE Geoscience Remote Sensing magazine, for which he has been also editor-in-chief between 2013-2017. And for concluding, is a fellow of IEEE. But then is, as I said, the lead of this wonderful project. So Lorenzo, the floor is yours.
Okay, thank you very much for the nice introduction. Can you confirm that you can see
Yes,
my slide?
I can, yes.
Okay, so good afternoon, everybody. It is a pleasure to be here to present what we have done in the context of this project on the Climate Change Initiative, which is focused on high-resolution land cover. As you can see from the logos that we have in this slide, this is a collaborative effort of many different research institutions with the collaboration of industry. What I'd like to do in this presentation is to give you an idea of the objective of the project, talking a little bit about the methodologies that we have used for the processing of our data, and then showing the products that have been generated and that then will be illustrated later and can be downloaded from the ESA website. Now, it was mentioned before that land cover is one of the main variables connected with the climate change. We expect that climate change may affect the land cover, and of course, changes in the land cover can affect the climate change in a loop. So it's very important to be in the condition to represent the land cover and the evolution of the land cover in a detailed way. Now, it was mentioned before by Clement that ESA has developed activities for generating land covers worldwide with a resolution which is in the order of 300 meters. This is very good for supporting, let's say, global analysis. But of course, when we look at regional situation, the resolution of 300 meters is not enough for the characterization of the spatial pattern of land cover. So what we have done in this project was to develop a series of methodologies and processing chain for generating land cover maps at 10 meters, 30 meters. So with an order of magnitude of improvement with respect to the medium resolution products. This in order to understand how the increase of the resolution can help in understanding the spatial pattern of the land cover and the impact on the climate analysis. This means that we have areas where we have extreme climate condition in which we need really to look in detail to the spatial pattern. And this is what we have done in the context of this project. Of course, facing many issues because when you look at high resolution data and your perspective is to analyze the data going back, like in our case, to 1990, the challenge is that you have to process many different kinds of data acquired by different satellites, and going back in time, this is becoming quite complex. Now, I'd like to introduce the area where we have developed our products in this phase of the project. It was mentioned before by Clement. After interaction with the user, what we selected are three subcontinental areas where the climate change has a significant effect. One area is in Amazon, where, as you probably know, we have a strong effect related to the deforestation, to the transition between the forest and to the agriculture, to the grass. And here we expect that there is an impact of this deforestation at the end on the carbon and water cycles. Another area that has been selected in collaboration with the community of the user in the surrounding of the climate change is Africa Sahel. This is an area which is interesting because we have that the climate change has a quite strong impact in terms of drought event, flood events. And there are also in this area some mitigation studies, like in the green belt, for understanding how we can recover some vegetation. Finally, we have an area which is in Siberia, completely different context, where we expect to see a movement in the area where we have the transition between the forest, the shrub, and the grassland due to the changes in the environmental, in the climate conditions. These are three areas of interest, and these are also three areas that are a very challenging benchmark for developing products because they are very different in terms of the behavior of the land covers, and also we have a very different amount of data available in this area from satellites. Okay, what we did was to have strict consultation with the user, the climate modelers, in order to understand what kind of land cover we have to represent in our products. And this resulted in the definition of the 16 classes that you can see represented in these slides, where we have different kind of land covers, different kind of tree cover. We have the representation of the seasonality for some classes. This has been defined by following the FAO Land Cover Classification System, LCCS, And this has been defined by merging the wishes of the climate modelers and what we think is feasible with the available remote sensing data. Of course, we are in a condition in which going back in time, the amount of data that are available becomes very limited. So in order to model the seasonality of the classes and the details, we don't have enough data, which means that we defined the land covers, the legend on the basis of what is really affordable. Anyway, at the end, we have 16 different classes, so quite a large number of classes to represent. Now, what we have done is to generate 3 different kinds of products. Of course, also in this case, taking the input coming from the user. One product is related to a land cover map that has been generated for 2019 only. This is at subcontinental level for each of the area and with a resolution of 10 meters. Then what we have done was looking inside this subcontinental area, selecting a large region of interest where generated some series of land cover maps between 2019 and going back to 1990. Every 5 years, we generated a land cover map. And then when possible, we also generated land cover change information on a yearly basis. That is, in order to be able to locate when the changes between 2 consecutive land cover maps occurred in time on a yearly scale. This is what we have done. And of course, for doing this, we had to implement 3 different processing chains. Now, I don't have the time to enter in many detail, of course, but I'd like just to mention here that we had a couple of major challenges to address. First challenge is that we had to analyze multi-sensor data. We had to consider, in order to have enough data, optical data, multispectral data, and SAR data. That is images acquired by synthetic aperture radar. And we had to do this by using different kinds of satellites, because going back in time, of course, we had to base our analysis on older satellites mission. This means that we had to process very heterogeneous data in terms of sensor, in terms of satellites, and also in terms of coverage, because in many cases, we had a coverage that was very limited and anyway very irregular in the different areas that we have selected. The second challenge that we had was related to the label data for the training of the system. We had very few label data with high reliability, and what we could do was to try to define this data by photo interpretation. This, of course, is challenging, especially when you go back in time, because it becomes difficult to understand the condition since it's very difficult to have any reference information. And so this means that what we had to do was to try to merge label data by photo interpretation with label data. That is, data coming from other products, maybe analyzed in a quite clever way for extracting reliable information in order to perform the training of the system, and as we will see then later also a little bit of validation. Well, I was mentioning we have 3 processing chains. The first processing chain that we have developed is the one for the generation of the land cover map at 10 meters resolution. Here, what we did was to use the data time series of Sentinel-2 and Sentinel-1 data, so SAR and optical, and we implemented the processing chain with 2 branches, one for the optical part and one for the SAR part. What happened is that, of course, the implementation required to implement all the pre-processing steps, many of these quite challenging, especially on the optical side. And then what we did was to perform classification of the optical and the SAR, and then the fusion. We analyzed different possibilities for classification. We started the project in 2018. We analyzed the possibility to use deep learning, convolutional neural networks, long, short-term memory networks, because we are in the condition in which we analyze time series of data. At the end, however, we decided to use shallow machine learning, and in particular support vector machine classifier for the optical data, since we are in the condition in which we have very limited training data. And then going back to 2018, it was quite difficult also to identify proper infrastructure based on GPU for the processing of the petabytes of data that we have analyzed. On the SAR side, we used some specific detectors for some classes that are typically characterized by SAR, like urban and water, and then a random forest classifier. Then we fused everything with the decision fusion module based on the use of Markov random field, and we generated then the map after harmonization that represent our line curve. Well, the second processing chain is the one that go back in time. We are in the condition in which what we have to do here is to process optical and SAR data of the old satellite, Landsat 5, Landsat 7, 8, 4, and also other ERS1 and 2, so very heterogeneous data. We had to change in this processing chain that has the same structure of the previous one, of course, the way in which performing the pre-processing, taking into account the different characteristics of the data. And then the classification was again done by using support vector machine and random forest methods, plus some detectors. But the decision fusion in this case was done by using a cascade paradigm. I'll mention a little bit more in detail in the next slides. The idea is that we take into account when we produce time series of land cover maps every 5 years, the temporal correlation that we have among the data. Okay, this is an example of what we have done in the pre-processing. In the pre-processing, what we did was to be in the condition in which we analyzed the time series of data with the optical sensor and generated a monthly composite for the production of the land cover map at 10-meter resolution in 2019. We used Sentinel-2 data, and we generated one meta image that represent the spectral signature for each month in order to be able to represent the temporal variability. Then what we did was to use a different approach going back in time because we have less data, and we used a seasonal composite. That is one meta image for each season in order to represent the variability, taking into account that the number of images is reduced. Okay, there is then a third part of the processing chain. I was mentioning this is a quite complex project. And the third part of the processing chain is the one devoted to the change detection. What we did here was to identify with the post-classification comparison approach the changes, and then on the basis of the time series derived on an yearly base to locate in the year the presence of the changes. Which means that at the end, what we generated is a map where we have the location of the changes on a yearly scale when the changes are present between the maps. Well, just one detail. What we have done was to work on the representation of the information considering a cascade paradigm. I think this is quite interesting from the methodological perspective. Here you can see a very simple illustration. I'm representing some pixel generic of our images for 2019, when we have 10-meter resolution in our images and in our map, and for 2015 and 10, when the resolution is of 30 meters due to the sensor. Now, what we did was to establish a relation among the product in 2019 and the product going back in time. And of course, this means that at 30-meter resolution, we have a correspondence with the 3x3 pixel for the 10-meter resolution. But then we modeled in the classification the correlation among the different times in order to generate land cover maps according to a cascade mechanism. That is, we use the Bayes rule for cascade classification implemented in the framework of Markov random field and the machine learning algorithm that derive the probability that we use for the classification. On the top of this, we considered the information on the changes. When we detect changes between 5 years, we analyze in detail and we extract the information on when the change occurred on a yearly basis. By the way, this information helps us also to limit possible errors in the classification. At the end, we have generated the products that you can see here. The static map for 2019 at 10-meter resolution has been generated in the green rectangle, whereas the regional land cover maps have been generated in the orange rectangle. And we have generated the products, but not only the maps, also a lot of additional information that you can download, which is related to the uncertainty of the products. For example, we have the representation of the land cover, but we have also the second class on which the classifier was undecided. And for each pixel, you know what is the best class, what is the second class, and what are the posterior probability associated with this class, so that you can process the data if you have to use in any modeling, take into account all the uncertainty. We have also uncertainty related to the quality of the input data that now I don't have the time to present. I show some results of the products just for the characterization of our products. You can see here an example of the map that we have generated at 10-meter resolution. We are in an area in Siberia. This is an example of the product at medium resolution, 300 meters. This is a Google image for reference. You can see that we can get, when we increase the resolution, a completely different condition with respect to the landscape. There are some classes, like the water here, that are not identified in the medium resolution products, of course, for the 300-meter resolution. But these are very important for modeling the details that we have in the area. This is another example where you can see, again, the comparison of a medium resolution land cover map against what we have produced at high resolution. There is one order of magnitude of difference in resolution, and you can see that what you see here is completely different. Okay, of course, this is something which is very important also because what happens is that if you try to aggregate the classes and to move this representation at 300-meter resolution, you don't achieve the same proportion of the classes, which means that changing the resolution changes also the results on the proportion of what you get represented in land cover in a given area. This is another example in Africa, where again you can clearly see the differences. We are in the condition in which we can get much more detail and also to identify classes that are not detected when we move on the product at medium resolution. I show another example introducing in the comparison another product, which is an ESA product, which is called World Cover. This is a land cover map of 2020 that is produced at 10-meter resolution. This is again the map at medium resolution. This is what we produced. You can see that one of the features of our product by design is that we'd like to preserve the fine details in the map. Fine details in this example means that we can identify the river, which is very important, of course, if your purpose is to analyze the climate condition. We applied a very limited, let's say, regularization against what has been done in other products. So we have more detailed maps, of course, with a little bit more of noise. These are other examples that I don't analyze in detail, but you can see the comparison between the products that we have generated with the seasonality of the classes at 10 meters and what is generated in the case of World Cover with a completely different target, of course, in terms of user. Well, here you can see an example of what are the products when we move from the 10 meters to the 30 meters. These are time series of land cover maps that span from 1990 to 2019 with a step of 5 years. We are here in the Khartoum city in Africa, and you can clearly see how with this kind of products you can get very clearly the urban growth, the expansion of the urban area. By the way, this map have a resolution of 30 meters. You can see here the scale is between 0 and 20 kilometers. So we have a lot of details for the characterization of this expansion. And this is another example, which is quite dramatic in terms of the effect of the deforestation in Amazonia. And this is an area, again, a very large area. Here the scale is between 0 and 60 kilometers. These maps are at 30-meter resolution, and what you can see is the strong deforestation and the conversion of the forest to grassland and cropland. which is the fact, of course, that we know is happening in Amazonia, but now we are in the condition to characterize in a very detailed way, also because we can capture also small changes that then, when grouped, have a very important impact in terms also of climate. This is an example where what we are doing is to represent the changes that occur on a yearly basis. So when we analyze two maps every 5 years, we are also in the condition, when data are available, to analyze when the changes occurred on the ground. This is a zoom in the area that I presented before on Amazonia. And you can see that with this kind of product, we can locate when the changes occurred, which means that in this example, we are mapping the changes between 2005 and 2010. The changes occurred, the deforestation started in 2006 in the green area. Then we had the expansion in the violet area in 2007, then 2008, 2009 in the red area, and the last part, the forest, that was in 2010. Also, in this case, we have associated the information on the probability of change, that is, the reliability of the change with respect to the considered algorithm. Okay, we have done an analysis in order to validate this product, and this is something that, for example, you can see here, looking at some Google images that show that the sequence of detection of the changes and the association with the years is something that is properly captured by the algorithm, because what we can see by a visual analysis is that indeed what we represent is in line with what happened on the ground. Few words on the validation. We have done validation. There was an independent quantitative validation. I was mentioning it was very difficult to get label data. So for the validation, we used two different approaches. One was based on the intercomparison with the existing products after having got the agreement. So with a quite structured procedure that has been developed by the Polytechnic of Milano. And then we were able to perform validation with this intercomparison by using more than 93 billions of samples. So very reliable in terms of number of samples, of course, a little bit less in terms of the certainty of the labels. You can see the numbers in the three areas that we got for this intercomparison of 8 classes that could be represented. Then we did some analysis by photo interpretation, and for getting also the classes that are the seasonal classes more difficult to represent. Here we have a limited number of samples, slightly more than 1,500. And so a large uncertainty, but these are the numbers that comes out looking at the 16 classes. And these numbers, we are sure, are affected by large uncertainty. So it's very important for us to get feedback from you if you are interested to use this product in order to understand what is your feeling with the quality of the products, since the quantitative validation has some limitation, as I explained. We use a huge number of data for generating the products. Okay, I don't have the time to enter in detail. What you can see here are the number of tiles of the different satellites that we processed. This is a huge number that is transformed in a larger number when we apply preprocessing, feature extraction, and then classification. So we are talking of petabytes of data that have been processed in order to generate the products that have been created in the context of this project. Well, so I come to the conclusion of the presentation. I tried to show you what we have done in the high resolution land cover project, which is something which is still alive. We are now in the phase 2 of the project. We have developed a processing chain that is based on 3 main components for the generation of high resolution land cover maps at 10 meters, then for the generation of time series of land cover maps at 30 meters going back to 1990, and then we have the change products. Of course, what is important from the methodological viewpoint is that everything is consistent in the data set, and we use this cascade paradigm in order to control the consistency and exploit the temporal correlation in the generation of the products. Then what we have done was to understand the limitation that comes from the availability of data. For some areas, especially in Siberia, the data available were very limited, and with optical data, as you can imagine, in Siberia, we had a lot of cloud cover. So this means that the products are associated with uncertainty information in order to be sure that you have also the information that tell you how much each pixel is certain in the output of the classifier. And what we have seen is that when we work at 10 meters, 30 meters, we can capture pattern of classes that are not visible as expected in medium resolution and cover products. And this is something that also is interesting, because when you aggregate the classes and you perform a degradation of the resolution with the high resolution map, you are in the condition in which you arrive to proportions that are different from what we see in the medium resolution products, which means that there is an expected impact which is quite significant also on the climate modeling. So we are now in a phase in which we are developing further the project, and what we are doing now is to try to take a lesson learned in the first step that we have done in the past 4 years. And this means that we are updating the processing chain. We are considering now the possibility to use also deep learning for the classification, since now there has been a significant developments also on the weak learning strategies for this kind of algorithm. So we are considering the possibility to use hybrid strategies and to consider deep learning architecture. We are also trying to extend the covered areas, and we plan, of course, to update also our time series of products. And let's say that on this, we'd like to have feedback from the user on what are the areas that are more interesting for your research, and having a feedback in general on the quality of the products that we have generated. That's a reason for which we'd like you fill a questionnaire. You can see the link here to the questionnaire. That is very quick to fill, but that is a way for providing a feedback to us, a feedback on the interest of the products, on the possible application you have in mind, on the extension of the products to different areas. That's something that will be really very relevant for us. And then, of course, if you are interested in following our developments, you can join us and be in our mailing list, so that when we generate new products, you are informed, or you can contribute to our workshop using our products and providing feedback. Feedback for us is something which is very important, of course, for controlling the evolution of our activities. Okay, I think I can close here. Thank you for your attention, and then if you have questions later, I'm of course happy to answer.
Okay, so thank you, Lorenzo. Was very clear, and I hope that it was useful for everyone. Also, not only for knowing what is available, but also the procedures that are behind that and all the study. It was really, we can say, a journey where we learn by doing, and we want to go ahead exactly in this way. So please consider what Lorenzo says, contribute to our project with suggestions, with checking the quality of the data we produced. I want to say we, because I'm very proud of being part also of this project, and thank you, Lorenzo, for leading it in a so well way. So, but you mentioned the possibility of downloading the data and using the data. So now in the last part of the presentation, we have one speaker telling us about how it is possible to do that. So I'm very happy to introduce now Massimo Zanetti, who received his Master of Science degree in mathematics from the University of Ferrara, the Department of Mathematics and Computer Science in Italy. and a PhD in Communication Information Technology from the University of Trento, the Department of Information Engineering and Computer Science. Now Massimo is a researcher in the Remote Sensing for Digital Earth unit at the Fondazione Bruno Kessler in Trento. His research interests mainly focus on mathematical models for remote sensing image analysis, with specific application to multispectral and hyperspectral change detection, time series analysis, variational methods for segmentation, and numerical optimization methods for image processing problems. His main contributions are related to the theoretical properties of tiling schemes applied to variational methods for large-size image segmentation, and the statistical approaches to image modeling and related inference in the framework of change detection. So very impressive bio specifically for a young person as you, Massimo, are. And very proudly, I give you the floor for let us know how to assess and download this data.
Oh, thank you, Maria. Very kind from you. And so here we are to the point of the webinar where we learn and see how to access the data and download them, and also a quick brief simulation on how to use them. So let's go to the steps. First of all, the main access point to all the information related to the CCI high-resolution land cover products and all the information is available on the project website, which is a banner from HISA. And this is you can see on screen the links. And you can access this site to get all information about the project, the deliverable documents, all updated to the latest version, to get all the details about processing chains, validation, and all the matter of information which is available to them, and especially the data. But let's go much deeply into the data download process. As Lorenzo already explained, the data are about three main areas covering regional to sub-regional region of interest, and they are available. All the data provided are available, and we have discriminated them between three different typologies of products according to their resolution and their purpose. 10-meter resolution products in the year 2019. 30 meters resolution historical products, so going back in time from 1990 to 2019, both land cover maps and land cover change detection maps. All the information related to the specific products, how to use them, and what are the details related to them, they can be found in these two quick documents that I have illustrated in the slide. The quick user guide for easy and quick access to the data, not too much details about quality stuff, and the product user guide, which is a full access point for all the information related to the process, to the products, including validation numbers. So let's go more in detail. As many other products from ESA CCI activities, the data is available through the CEDA, the Center for Environmental Data Analysis, based in UK, and you can access them. If you are already accessing the data from other CCI projects, you already know this, but I'm assuming that we can start from scratch. From the SIDA website, we can start our process for registering so that we can have all the information available after successful registration. So after accessing this link and successfully get a login, username and password, you can go to the ESA CCI high resolution land cover data available to the source. Here is the link. And here we have a brief description. You already know spatially where the data are and the kind of distribution in time, the kind of typology. And here is basically the database structure in which they are organized. There are the three main folders, repositories for the three main areas, and each of these folders is structured in the same way, as you can see below here. There are the historical products and the static products. And going down to the tree, we have land cover products, land cover change products at 30 meters, and land cover 10 meters for the static products. For each one, we have both a mosaic data, which includes the spatially jointly images, mosaiced images over all the reference area that we have showed before. And also we can have the tile data. So for each one tile is in the same scale of the Sentinel-2 products. If you are familiar to them, one side of rectangle is 100 kilometers. And they are all available even in a split mode in tiles. So how to get to the data? And let's say before some details about how these data are organized and let's say naming convention in order to navigate through them and knowing and being aware of what we are looking at. The file naming convention follows the ESA CCI standards. So we have a banner in the beginning of the string of the name, and then there are some placeholders, some fields that are specifically related to the parts of the data. Product type is the first identifier, which is split into three values. Map stays for land cover map, so the real land cover product, and it is identified by the string map. Then uncert, which are related to the uncertainty products. We already seen in the presentation given by Lorenzo, there are different products like classific second class, the probability, posterior probability, the equality index, and there are many. And they also change, which are related to the change products, land cover change products. Each one has a sub ID, let's say product ID, which is related to their specific definition into the product type kind of value. So for maps, we have class 01, which is the only one, the first class based on the ranking of the classifier. Then there are several values according to the uncertainty products, the second best class, which can be used for several purposes, studying the competitor of the best class for especially in uncertain areas. And then the posterior probabilities for both the first and the second class, and the high quality input quality index. And then the change detection, which is by itself. And there are other specifiers, the tiling ID, especially for navigating especially the data. For tile products, we have the same nomenclature of Sentinel-2, so a string which is composed by 0 to 01, 02, 03, which is related to Africa, Amazon, and Siberia. So this is the first identifier to get to the basic study area, so Siberia, Africa, and Amazon. And then the tile in the Sentinel-2 scheme, MGRS, Military Grid Reference System, which follows the same structure of Sentinel-2. For mosaic, there is a string called mosaic, which is the joint union of all the tiles. Then spatial resolution is as well identified, and then temporal frequency in years, and the epoch of the product, which is indicated with string of the year. So here are some examples to get familiarized with this data. This is the strings of the file names of some examples of the data. Notice that the files are GeoTIFF, so they are georeferenced and exposed in TIFF format. And they are all like that, and they are raster formats. So how to get to them? Let's go to this point. According to the different principle of SIDA and procedures to get the data, we can get them both singularly, picking one of them, each one of them through browser navigation, or to get them also in a more bulky way. So we get to get data in the main window, and we can Also, go to the option for boot download. The link is very little, so I have highlighted this because probably someone can not notice this. So here is information to get bulk download of the data and see what are all the procedures that are allowed from this archive. And later in this presentation, I'll be going just for two of them, and these are HTTP downloads and FTP downloads. So the other methods are probably less used, and if you are familiar with them, after knowing how to do with HTTP and FTP, you already have the information to go through the other methods. And also for time constraints, I cannot go through them through all of them. So let's start just by looking quickly how to get data by HTTP. The first way is the simplest one. We can directly access the repository, which is available through this link, and we can manually navigate through them. You already have in mind the structure of the data, which I have showed before. Just by clicking one link after the other, you can get to the places where data are available, and after that you can download singularly each one of them. Please remember that the mosaics, like in this case, they are very big. They can take some time to get downloaded. And this is by the compiled HTTP website. There is another way to go still through HTTP, but with raw data. So you don't have the interpretation of the browser, and it is written in plain HTML, and you have access to the same data. The structure is the same. There is just no fancy coverage of the website. So here is the same data reached in this framework. Of the difference in the link to reach this place is just the suffix in the hosting web address. So the AP instead of data, as you can see. Both of these are going through the browser. We can, for example, I can try to simulate this very quickly. I'm sorry, getting out this. If you can see this window, here is the web. See the web archive. We are going to the plain HTML interpreted page, so we can go through this. Clicking Amazonia, for example. Let's go. We want to see static products. We can go through all the three. Let's say we want to see tiles. We have available only 2019 here, and here are all the data here available. All the places can be reached from here. And let's go to the raw HTML. The same works for this. Probably a little quicker because the page is not interpreted, but we can reach the same place as before, going through the information. And here is, just by a quick click, we can download the data. Okay, let's go again to the presentation. Okay, now to get access with FTP, so to have more control on the downloading process, we need to be get from SID archive a reserved password, which is not the same of the login that you have already did before. We have to start the process to get the FTP password. So from this page, under Tools, you can see in the banner above the page, you can click on File Transfer Protocol and then go into the page. We have access to My SEDA, and then we have to go this page, clicking this link to go further. Here in this is your home account in the SID archive. You can go to My Details and then configure FTP account. Clicking inside here, you can get you can start a request for getting the password for the access of FTP website. For the FTP access to the hosted resource. So once you get the password, you can access to an FTP client of any kind of your preferred one and go to the ftp.seda.ac.uk. And using your username, the same as your login, but the FTP is the password to get to the access. So here is an example of, here I'm using WinSGP, but almost any FTP client is pretty much the same. You can get to the data very easily in this way. And in this way, you can browse the data and download the picking or also sorting out the data with search with wildcards, or even if you access by command line interface, it's even easier to get this kind of analysis to get the specific data of your request, like for example, browsing with tile code information or something else. Okay. So once you got the data, how to actually look like, make them look like as we've seen in the presentation. Pretty easy. We have information available to do this. You don't have to build yourself the legends or something else. Here is a simulation I can show you in QGIS, Quantum GIS software, which is open source and freely available, very effective for remote sensing data, as in this case. And here in this little procedure, we will go through download of one products and then download also the land cover maps, colors, and then we will see how to make them work in QGIS. For the sake of the, okay, let me just review the steps. First thing, we can go through this location where we have the metadata information of the land cover colors. Let me show you, for example, in the location over here. To the link that you have, you see in the slide, you can reach this place where you have metadata available. Then you can click on QGIS Legends, and you have three different ones. One is for land cover, one is for land cover change, and one is also to understand the past classification comparison. We will not go through this, but let's just go to the land cover one, for example. To get them downloaded, you can click on it and then save it as a text file in your computer. I already did it. This is the text file for indexing land cover colors. Once you've done this, you can open your QGIS application. Let me import QGIS software over here. So I have already a file downloaded on, let me see over here. This is the one file that I previously downloaded. I can drag and drop over here. The default showing option is grayscale, but we can do better. So here is it. And after having selected the products over here in the layers banner, we can right click there, properties. Let me show here. Let's ask for visualization in unique values, as classification does. And here on the bottom of this window, we can upload our load color map from file. We can upload our requested file, which is the land cover map text file over here. Here is the legend, as we have already filled, and we can apply it here. Here is the product, and we can also query some points just to see that the value of the map is the legend code, as we see, 17 for grass, forest 10, and here is it. Some urban over here. Yeah. Here is the basic stuff about how to get the data and how to use them. And of course, if you have any questions, we can develop it even further, but that's actually all from me.
Thank you. So thank you, Massimo. So thank you all the other speakers before. Now I want to call you here, Lorenzo, Clement as well, because I see that there are some questions for you. So the first question is very easy. So will you give available your presentations later on?
I'm very happy to provide you a PDF. Yes.
Fantastic,
Yes,
fantastic,
same
because
for me.
people, they wanted to have your presentation. Also, I believe that Massimo can give his presentation. Massimo
Of
is
course.
too?
Yes, 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 of
Okay,
course.
very good, very good. Then I have a question that probably is for Clément, I believe, because the question is, will the CCI land cover data also be on Google Earth Engine? And then the second question, will the data be made with global coverage? And I'm also interested in this second question.
I mean, the first question is a very interesting one. My opinion is that data should be available where users look for them. So that give you an idea of my answer. For the second question, I would also be very interested to eventually have a global coverage of high resolution land cover with sufficient time back in history, but now it's also for the team to tell me what is possible. So it's a dialogue we need to maintain together in the coming months, in the coming years. But I'm all in favor.
Okay, thank you so much. But Clement, before giving the word to Andrea, because I know that Andrea has also a question, but I want to better understand what is the value of this variable, land cover, with respect to the climate change.
Thank you, Maria. Yes, that's a very important question. Accurate estimates of land use and land cover change are crucial to support the Paris Agreement and its process of the global stocktake. For policy purposes, parties to the UNFCCC, they are required to submit statistics on anthropogenic greenhouse gas emissions and removal. And their definitions of anthropogenic greenhouse gas emissions include different categories: the fossil fuel emission, the industrial processes and product use, and the emissions and removals arising from changes in land cover in what we call managed landscape. And for greenhouse gas inventory, following the IPCC guidelines, the concept of managed land is used as a proxy for anthropogenic effects. So we need to have accurate estimates of land cover and land cover change across country. And once we have mapped or quantified by area this land cover data, we can combine them with, for example, emission factors to allow greenhouse gases due to land use and land use cover plus forestry to be computed and included in national inventories.
Okay, thank you. And Andrea, yes, I know that you are curious about something, so please go.
Yes, I also have a question because I am working in the ITU Radio Communication Bureau, and for radio communication purposes, land cover information is instrumental for improving the precision of some path-specific propagation models, which are needed to evaluate the signal coverage and for interference analysis. Well, what I would like to ask you, if it is feasible to build up a worldwide DEM and land cover data sets where for each pixel we can have the information about the bare earth height, the type of the cover, and the height of the cover. Concerning the resolution for rural areas, 30 meters would be enough, while for urban areas we will need to go down to a lower to a resolution which would allow to see buildings like 5 meters. So which are the complexity of these tasks with respect to what you are doing already right now?
Lorenzo, you want to answer? Do you want to answer? Yeah.
Yeah, I can try to answer. The question is quite structured in the sense that you are interested in digital elevation model at high resolution and then in the land cover at high resolution. Of course, what we have done in the framework of this project cover the part of the mapping of the land cover. I mean, we are in the condition in which we have processing chain that have been tested on some benchmark areas, could be extended. It was also asked before about the coverage. Of course, this is something that can be done. I guess that in your case, you are more interested in a static representation. You don't need to have the time series. I understand that probably you need also some to capture some of the details of the land cover. So probably what we are doing is in line with what is the expectation for this kind of application. Of course, there is the point of the digital elevation model that now there are data that comes from TandemX mission, TerraSAR-X that are associated with, I think, a global digital elevation model at high resolution that, okay, could be a point to consider. There are lower resolution digital elevation models that can be easily used. And yes, in terms of the situation on the urban area, you have to change the sensor. If you need 5 meters, you cannot use the Sentinel sensor, the Landsat sensor. You have to use other kind of systems. I mean, you can try to use planets or you can try to use worldview. There are different type of commercial satellites that provide the data. So it's feasible. Technically, it's feasible. Of course, there is some work to do. And I would say that for the land cover mapping, what we have done in this project is a good starting point for getting that kind of information with the right details. But of course, this is a good example on how this kind of product has been developed for climate, but can be used in many different directions. When we talk about land cover, of course, it can be used in many different applications.
I thank you very much.
Yeah. So if I can comment, Andrea, if you want to stay on 10 meters resolution, the open data is perfectly fine. If you want to go down the 10 meters, so probably you need to have also commercial data, commercial satellite data, and therefore, if you want to buy this product, it will be more expensive. That is the point, because those data are not openly available.
Yeah. Yes, I understand this, but let's say we want to stay on the open data. So let's focus on the 30-meter resolution or even.
No, you can go to 10 meters resolution.
Yes,
you don't
yes.
need to stay on 30,
Okay.
because with the Sentinel now we can go to the 10.
Okay, but then what you okay, so we will be able with this pipeline that has already been established with some modification to be able to say, okay, that amount of height is the cover and that amount of height is the bare earth ground.
Well, this is a little bit more complex, I mean, because you are talking of getting the elevation. And of course,
yes,
if you take a digital elevation model, what you get typically is the elevation of the ground. You can put on the top of this the land cover type, which is something that can be done following a processing approach similar to what I have described. But then if you need additional information on the vertical structure of what is on the ground, that's a different story, because you need to use a different kind of sensor and systems. So let's say that you can get the background in terms of land cover on the top of the digital elevation model of the ground.
Right.
Of course, depending on the class, you can have some guess on the elevation, but this is not a direct measurement.
Right, because I believe that as an example, SRTM is giving the elevation of the bare ground plus the cover. So we will need to estimate how much of the cover height, or have some additional data sets to distinguish the two. Okay, I thank you very much for this clarification. Thank you.
Yeah, and I want to consider the very last question because we are a bit late. So the very last question is for Lorenzo again, and it is more related to the processing. So the question is, if you use a unique methodology everywhere for processing using machine learning, because we saw that is you use the machine learning. So if the model is the same everywhere, or it needs to be customized region by region.
Let's say that the model needs to be tuned on the different regions, also because we have a completely different behavior of the land cover. When you look at the time series, for getting, for example, seasonality, what we have is different in Amazonia, in Africa, Sahel, and Siberia, of course. So this is something that requires some specific tuning. What we did, by the way, was to use also the climate zone in order to define models that are adapted to the different climate zone. So what happened is that, of course, in each of these areas, you can identify different conditions on the climate that affect the behavior of the land cover. And this is an information that we used, which is available, that we used for optimizing the tuning of the methods. And of course, this is something that could be generalized then in the idea to go on a global coverage.
Okay, so thank you, Lorenzo, for answering also this last question. And I want to close, before giving the word to Andrea, I want to close thanking you all and recommending all the people listening to this webinar to contribute to this project, downloading the data and checking and testing the data. As Lorenzo said, it is super important that you contribute to this project because it's meant to be a global project. So we need to have also your feedback, specifically if you are living in that area and you know much better than us those areas that are involved in the project. So thank you so much in advance to you if you can help us. And with this, I will give back the floor to Andrea for closing this fantastic section. Thank you.
Thank you very much, Maria, for having moderated this event. And I really also want to thank Lorenzo, Massimo, and Clement for this webinar. It was really very much informative and really very clear. I want to remind you also that this presentation is available in the neural network, so you can download it. You will be able to download it, and of course you can watch the recordings of this webinar on YouTube and in the neural network. I also want to thank the audience for the active participations. I finally want to remind you the next planned events for the GUI Discovery Series on April 11th. We will have NASA IBM to present their Geospatial Foundation model. And of course, I want to remind you the workshop, the For Good Summit on May 30th on navigating GUI, plotting the course for future education. This is a workshop organized under Maria leadership. Participation of all stakeholders from academia, private sectors, United Nations. We showcase the deliverable of the 4 international working groups, which were set up following the GUI workshop, the For Good Summit in 2023, which really highlighted the need for establishing educational frameworks in GUI. So stay tuned for these exciting developments. Enjoy, and I thank you all again for your participation. And with this, let me give back the floor to Anna. Thank you very much.
Bye. Thank you. Bye.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.